Hello everyone, welcome to pipebench.com. For regular load analysis for buried HTTP pipeline, we have developed a separate tool based on AWWA M55. That tool should be used if your surface loading is less than H20 for vehicles or less than E80 for railways. However, that is not always the case. Sometimes you will have HTTP pipe used on mining sites, or it's going to cross a haul road. So in that case, your vehicle loading that for your design will be a lot larger than H20 loading. So in this case, we have developed another tool based on similar theory, but we slightly changed the way we calculate surface loading based on the Timoshenko equation. So in this way, we can have a way to estimate the surface loading from a way bigger vehicle. So next, please allow me to use an example to show you how to use this great tool. Similar to the other tool I was talking about, so for the pipe input data section, it's pretty much the same. We have a drop-down menu for you to select the typical pipe dimensions, size, DR number. So in this case, we can say is IPS pipe standard. We have let's maybe assume it's gonna be a smaller pipe, let's say 16-inch. Assume gonna be a DR11, P7010. We're gonna use long term, however, to do the design. So like I said, this pipe input data section is pretty much the same. Coming to the load input data, the first half is pretty much the same too. We can put the soil unit weight, depth of cover. So in this case, we can assume it's going to cross a haul road is let's say 3 foot deep, and the trench width is 16-inch. So yeah, 36-inch width is fine. Trench embedment soil type, let's say we assume the fine grained soil, so that's less than 25% sand content. Let's say we don't do a lot of compaction. We'll see how that goes. For native soil, let's say it's going to be very loose, granular, and soil cohesive. The wheel load section. So this is what is very different from the regular tool based on AWWA standard. So here we will need to take a look at the actual vehicle, the largest vehicle going to travel on that haul road. So for this example, I would like to use, assume this is going to be a very large mining truck going to travel on that haul road. This is one of the biggest truck we're probably going to see on the mining site. Is CAT 797F mining truck. As you can see, is a huge truck, and so this is the vendor supplier website. There's always has a specification section, and in this section we're particularly looking for 2 parameters. One is the weight, and another one is the tire info. So let's scroll down and see there is a weight section, and we can see they have body weight, they have a chassis weight. This is a target gross machine operating weight. So this is typically what we can assume for the total load from the vehicle. However, this is the total load. It's going to be evenly distributed to different wheels, and then we need to find it out the weight distribution data as well. So if you scroll down, usually they will have a percentage of the weight distribution here. Weight distribution approximate. So we can see the front axle, which is the front 2 tires in total when it's loaded, is 33.3%, and for the rear axle loaded is 66.7%. Basically, it's 1/3 will be in the front 2 tires, and 2/3 will be on the back 4 tires. So you can see from the picture, there's 6 tires in total. So here we go. Now we know for the real excess loaded case, there will be 2/3 of the weight gonna be on the back, and we basically gonna just calculate the weight based on this information we have. As you can see from the picture, there's 2 tires on each side. So we're basically gonna assume it's 2 tires as a 1-point load for the calculation. And so that way, let's find the number again, 1,375,000 pounds times 2/3 and divided by 2. That will be how much weight when it's loaded for each of the 2 real tires. So I did the calculation on the side. So we are talking about per real side. Like I said, there's 2 tires we consider as 1 wheel load. It's gonna be 458,563, roughly like that, as the maximum point load. Okay, so now we have the load info. The next information we need to find is about a tire. So we need to know how much contact area of these 2 bigger tires would take to the area. So that is the wheel load areas we're gonna use to put in the calculations. So we scroll down, and we need to go to the section about tires. Here we go. So this is the tire section. Usually people, some of the equipment that will give you the tire information, but here they just give you the tire model number. So we can go to the website to further identify the tire's dimension. So in this case, I have checked the Bridgestone website and find this tire, and I think it's this one. So this is the one was showing on that specification, equipment specification, and we can further double check is that's exactly the same size. And as we can see, overall width of 1 tire is 57.4. So this is the width. So we have 2 of them. We need a 57.4 inches times 2, and also for the length of the footprint. So this is going to be determines many factors, like how heavy the truck is, what's the pressure in that tire. But usually, what I typically do is I assume is roughly half of the overall width for the length as an average number to calculate the wheel contact area. So let's come back to the calculation tool here. So in the wheel contact area here, so I did some rough calculation. We have 57.4 inches for each tire, and we have 2. We need times 2 to get the overall width. And for the tire footprint length, I assume 30 inches. So in this case, we get the total wheel contact area for the real side on one side is roughly 24 square feet. And here's the impact factor. We can typically use 2.0 or 3.0. In this case, maybe get a little bit more conservative. Let's go for 3.0. And then we scroll down to the output sections. For design parameters, like the same thing as the other tool. We basically can show the OD, batting factor, 0.01 is typical. We don't want to change that. Time lag factor, 1.5, very typical. We don't want to change that. The way we calculate the soil parameters to calculate the soil load, it's pretty much the same as the other tool. So we calculate the modules of embedded soil reaction based on the embedment soil type we selected, modulus of native soil reaction based on the soil type we selected, soil support factor also depends on the trench dimensions. And then coming over here, we have a design modulus of soil reaction 500, soil load, this is all the same. The live load, as you can see, is much bigger than the H20 loading we were talking about for the other tool. And come down, the surcharge load still seems 0. There's no structure near the hole road. And the maximum allowable pipe deflection is 5%. Now let's take a look at the results. It's a 49.35. This is almost 10 times more than the pipe can handle. So there's only a few ways to make this work. Let's take a look at the trench design first. So first of all, apparently 3 feet buried depth is too shallow for this kind of massive equipment to drive on top of it. So let's go a little bit deeper. Usually it's going to be help to reduce the surface load greatly. So in this case, let's go to 6 foot. And the trench width, we can go a little bit even bigger to make sure we have high quality soil around the pipe, more quality soil around the pipe. And here we can go to maybe the coarse grain soil with fines. We're going to compact it really well to 95%. Native surround soil cannot change that. We don't want to change the wheel load and everything else. Let's come back. Look, the deflection has been changed into 10%. So it's a great improvement, but not good enough. So a few other things we can do. We can either go a little bit deeper. Let's say we go to 8 feet. And then we can maybe use a thicker wall to cross the hallway, because a thicker wall will help to reduce the deflection. And let's keep everything the same and come down over here. 5.53%. Still failed. Okay. And then we can keep going to have a deeper cover. Or let's try maybe compact a little bit. We don't want to have too deep of a trench. In this case, we are barely at the edge here. It's still showing fail, but it's like almost getting there. So if in this case, we just need to go a little bit, maybe a little bit deeper. And here we go. So in this design, because we have to manage the load from this big mining truck, we end up using a very thick wall pipe and very deep. We use pretty high quality embedment soil. We have to compact it very well to 100%. And that's the only way we can make everything work. So after making sure everything's fine, then we want to generate a design report and to provide to the group. So we can just use this report button, and you can put all the project information, dates, revisions, who develop it, who review it, who approve it. And then you can generate a PDF report that has everything. You just put it in. You can file it, you can save it. So it's very nice. One more thing, like all our other tools, we offer metric version as well. So once you click metric button here at the top, and then all the inputs and output data will be in metric units. And as you can see, everything is already converted by itself, or you can use the metric system for input at beginning if you're working outside of the US. And if you does that, then when you generate a report, everything will be in metric units as well. Okay, that's everything about this great tool. If you have any questions or you have any suggestions, please visit our website, pipeng.com, and leave us a message. We look forward to hearing from you. Thank you.